Welcome to my channel. In this video, we are going to work out the far field expression for an array of two hertzian dipole antenna. The hertzian dipole antenna is lying down horizontally, pointing to the y-axis or x-axis. We are going to examine each of the cases. Okay, so we have an array of two infinitesimal horizontal dipole antenna positioned along the z-axis. The distance between two antenna is d, and beta is the progressive phase shift. And the far field formula for one individual infinitesimal antenna is given here. Yeah, and this beta is just the beta in the antenna, but the antenna itself is horizontally mounted. So we have to change the orientation, and we should not assume this beta as the angle of elevation. Okay. Okay, done. Now we are going to work it out. So to begin with, we need to be very clear about the three-dimensional picture of the antenna. So let's say we have the three-dimensional space, z, y, and x. And let's say you have a antenna here. Yeah, make it ultra saturated. Yeah, it's pointing to the y direction. So obviously, the angle that we are interested in is this angle, right? This angle. Or let's assume this is C. And this C will be rotatable. It's not in the YZ plane. Now, let's assume that we have an observation point here, and this observation point is called C. Yeah, and let's say in three-dimensional sense, the perpendicular projection of this will create a circle, and this is a right angle. The angle here is phi as normal. Yeah, so the angle here is beta. Normally, with beta and phi, this is going to be enough to describe the whole picture of this setting. But in this case, we are given the formula for electric field. The formula is E sine C, and then E J K R. So this is the formula. There is an issue. We need to work out this, because the C here is not the angle that can easily be found from the three-dimensional system. We need to work out this one. We need to express sine of C in terms of theta and phi. So this is the trick of the question. Now what we can do is, we have shown the origin as all the this point is A here, this point is C, and if here is theta, then here is theta as well. So this is a three-dimensional case. Because C here is not in the same plane as theta. We do not have shown C to be the angle in the zy plane. Okay? So now let's work out here. This is theta and this is, say, hello. Yeah, then the value here is arrow sine theta. So this is the length. Length AO is r sine theta, and the length AC here is arrow cosine theta. There is nothing difficult, right? But we have to be very careful. Our job is not about this right angle triangle. Our job is to express C in terms of theta and phi. Because C is the angle between the pathway R and the y-axis. So let's say in here we can still draw the right angle triangle. So this, let's say this is B. Yeah, this is B. So triangle OCB is the right angle triangle. So if we work out carefully, we have only one angle here. So here should be arrow sine C, and here is arrow cosine C. So what is left is this triangle. Remember, this is a right angle triangle, right? So this is also right angle triangle. So if you look carefully from this side, then you know that A, C, and B is actually a right angle triangle with the right angle right at the corner A. The size here is equivalent to cosine theta. The size here is equivalent to sine here. So obviously the length here is r sine C square minus cosine theta square root. So this length here is equivalent to this length. Now, everything becomes clear now. What we need to do is to focus on the triangle OAB. Focusing on triangle OAB. We use the cosine rule. Using cosine rule, we get the length here square. So AB square equals to AO square plus OB square minus 2AO OB, and then cosine of this angle. This angle is obviously 90 degrees minus theta. So That's where the trick is. AB, as is given here, is AB square is sine C square minus cosine. AO is the length here. OB is the other length here. And 2R square sine theta. Sorry, this one should be AO. AO, yeah, correct. OB should be cos C. So cosine C, and then the angle cosine 90 degree theta. So it looks very complicated, but actually it's very simple. Sine theta. So we get rid of R, which is common in both sides of the equation. And I'm going to simplify this expression on the fly. So these two terms can merge together into one value, 1. And this term can go to the other side, and which end up with 1 cosine and cosine here will be equals to it's very clear now. Cosine C is equal to sine theta cosine phi. So this is a very important finding. Now, what we are going to do is to find out sine C, not cosine C, because this is what the expression should be. So sine C, according to here, yeah, we can work out from this line here, yeah, or from either way here. We can say this one, right? Or this one, right? So this one, right? 1 minus, so 2 sine C is equal to 1 or 2 minus 2 sine theta cosine C sine theta. So we have already worked out, yeah, this can be moved to here, and sine C 1 minus sine, yeah, this term minus this term, right, is sine. So this is what we get. So finally, we can replace equation 1 with this expression. So this is a situation when the antenna is pointing to is lying horizontally along the y-axis. So the condition is antenna horizontally mount along the y-axis or parallel to the y-axis. I hope this is clear enough. Okay, so we can continue. This is the basic concept we need to know when the antenna is horizontally oriented. The next thing that we are going to do is to find out the antenna array formed by two Hertzian dipoles, which are horizontally oriented. So this is the case. The y-axis. So we have two antennas, and both are in phase. It's too bright. Yeah, let's make it dark. So you have two antennas, and each one of them, the distance between two antennas is d. So obviously we have 1/2 d here, and we are looking at the far field. Say for example, the observation point is somewhere here, right? Very far away from the antenna. And we have shown this distance as R1, we have shown this distance as R2, and obviously this distance is R. And previously we have already learned R1 is equal to R plus minus D cosine theta. And R2 is R plus D cosine theta. That's what we have learned. Now, we are going to use the original formula for the electric field as detected from the observation point. So the electric field in the observation point, the electric field detected in the observation point is going to be the combined field due to antenna 1 and antenna 2. So E1 plus E2, and using the original formula, K₀ L, and then 4 pi R, and then 1 sine theta sine y, and then remember, right? Antenna 1 and antenna 2 are different in terms of the position. 1. And remember, we also have beta as the progressive phase shift. This is something that we have to address. So altogether, right, we have to, and another term here is J R2 So that's what I think. This is the combining electric field. But remember, we are going to use these two expressions for phase approximation. And for magnitude approximation, I mean this magnitude, R1 is essentially the same as R2, which is essentially the same as R. Yeah, if the observation point is very, very far, R1, the length of the pathway, R1 and R2 are basically the same. So for magnitude approximation, okay. So in this case, we are going to deal with the magnitude approximation first. Yeah, sorry, I need to remove the hole to dry. I hope this is okay now. Now, not very good. Just a minute. Okay, let's continue. So E is going to be K, and we have a common from here, and here we have K. We are going to substitute R1 and R2 using these two expressions. By the way, it should be -2 because the length here is -2. So this is what I can get. So if we further simplify this expression, we will get JKR plus theta. So this is the term, and then depends. If there's a minus here, this is easier to deal with. Yeah, let's say this is minus. Then what we are going to get here is 2 cosine KD theta over 2. So this is the final expression. The term here is the array vector. The terms here is the element vector. In this case, the element vector and the array vector will both contribute to the shape of the antenna. As a result, the directivity will be dependent on the value of theta and phi. Okay, I hope this is clear enough. This is the answer for one part of the question. And just now, I have mentioned that in the beginning, I have mentioned that the antenna is pointing to the y direction. But what if the antenna is not pointing to the y direction? The antenna is pointing to the x direction. And this is the case I'm going to show you. You don't need too much work. You just need just one simple concept. So in this case, I tell you how to work this out very easily. You just assume we have a similar setting. But we don't. We are going to interchange the label for x SS and y SS. So this is become x and this will become y SS. And we are going to do this. So essentially, your antenna is still pointing to x. Your antenna is still horizontally lined, but it's pointing to the x direction. The length, the pathway here will remain R1, R and R2, and obviously the height here is d over 2, and assuming that the observation point will produce a perpendicular projection, and in this case the angle here is phi. The angle here is not phi. The angle, the axial angle, should be measured from the x-axis. Just say in this case from x-axis to here. But this angle is measured from x-axis to somewhere between x and y-axis. And as a result, we should be consistent in this setting where x and y-axis are inverse. Then the axial angle should be measured from x-axis. So this will be the theta. So in this case, if you work out carefully, you will find out sine cos theta is equals to 1 minus sine theta square and cosine phi. This is the only change. And if you continue with this process, I can tell you the final electric field will be very similar. The final electric field in this case will be Ki0 4 pi r 1 minus sine theta cosine phi, and e to the power k kr plus beta, and then 2 cosine kd cosine theta over 2. So this is the only thing that you need to worry about. This is the only difference. The answer I have given in the PowerPoint is not correct. This is the correct one. Okay, if you have any question, please leave your question to the comment section of the video, or you just ask me after coming back from the tech holiday. Anyway, thank you for your attention. Bye bye.